I'm Matt Learn, and I'm going to see you guys with a short video. These are mine.
This is not a haphazard maneuver. Careful planning for it started months back. Don't worry about yourselves. As far as the test is concerned, you'll be okay.
For my project, I solved the problem, of how to turn fluid energy into mechanical power. To do this, I built a turbine, a radial flow turbine, based off of Nikola Tesla's design. So basically, what you end up with is a box with flat discs stacked, co-rotating. Fluid flows into the bottom of it and rotates the discs spiraling towards the center and exit towards the sides. I wanted to produce one that would be 1 horsepower, operate 5,000 RPM, and preferably be relatively quiet with a reasonable efficiency of 20%. To that end, I designed this turbine, which got 15 blades with 8-inch holes, 6 of them on the sides, 8 holes on the exit planes, with a nozzle that we go here. So, to analyze this, I originally started out with making it so I originally started analyzing it with fluid flow being a viscous flow, so you end up with a shear flow between the discs and the airflow. So that requires a lot of calculus that I don't know. After discussion with Professor Beardsley, it's decided that using the change in enthalpy would be far easier to use some of the pressure difference. The trick is, in order to do that, you have to know the isentropic efficiency of the turbine. So, upon some research, I found a paper that had developed a model based off of 6-dimensional parameters for a turbine. Basically, the parameters are pressure difference over the turbine, the outside diameter of the turbine, the inside exit hole diameter of the turbine, and the working fluid. Using those 6 parameters, you can develop flow sheets such as this. So you have the change in enthalpy here per degree of drop, pure degree of drop in temperature for air. You have the Reynolds number, which is based off of the mass flow rate, the spacing of the discs, and the working fluid. This is one of those dimensional properties that depends on the Reynolds number, and efficiency depends on the variable, which the problem with this is you end up with the mass flow rate depends upon the Reynolds number, and efficiency depends on the Reynolds number. There's no direct way to solve for this, which is why it's in the spreadsheet. So Excel can do an inverse solution and just try to repeatedly solve. This is based off of my design of turbine, which I ended up with predicting 18.8 isentropic efficiency for my turbine. So for the testing, you end up with a turbine here. You can't really see it, but there's a dynamo on this side, which is just a brake group that's fixed to the shaft. So as it rotates, the brake is stationary, held in place with a strain gauge, which is what that's reading, so I can determine the deflection in that. With MAC, I can figure out the torque provided to the shaft. And for the input side, you'll use a volume flow meter, temperature and pressure gauges before and after the flow read. The meter determined, because the flow meter is what you do have a 2% drop in pressure. The results were I predicted it would take 7 cubic feet of air per minute to ride 1 horsepower at 5,000 RPMs. It ended up taking 91 cubic feet per minute of air to only produce 0.1% horsepower, or 0.1 horsepower at a 4% isentropic efficiency, which is not good. For budget, I predicted it's going to cost about $500. I came in just over that, based off the fact that I didn't provide any budget for testing. But mostly I got that schedule. I predicted it would take 351 hours. It took 378 hours to do it, which is reasonable. Conclusion is this device failed miserably. The predicted falling flow rate of 7 meters versus the 91 cubic meters per minute flow rate meant that I ended up with about 5 times more back pressure to drive the air through the turbine, which meant there was less potential energy to drive the turbine. And there was no loud seals on the discs and the outer casing, so there was a lot of blow-by there. And my bearing fit was a little tight, so I dissipated a lot of power based off of the bearings. And the model is not 100% efficient. The paper that they tested, they ended up with somewhere between 5 to 10% error. Has that any questions on that?